Welcome to your Algebra 2 lesson 11.3. Today you're going to learn how to use normal distributions. A normal distribution is a probability distribution that is modeled by a bell-shaped normal curve. And here's a picture right here. The total area under the normal curve is 1. Areas under the curve represent the likelihood of outcomes within the range of the appropriate values on the horizontal axis. The empirical rule states that for a normal distribution, 68% of the area is within one standard deviation of the mean, 95% of the area is within 2 standard deviations of the mean, and 99.7% of the area is within 3 standard deviations of the mean. The mean is always in the center of the normal distribution. Okay, let's look at an example of how this is used in real life. The scores from an IQ test follow a normal model with a mean of 100 and a standard deviation of 16. For part A, we want to draw the model for these scores. Clearly label it showing what the 68, 95, 99.7 rule or empirical rule predicts about the scores. Okay, so what we're going to do first is determine where the boundaries for 1, 2, and 3 standard deviations from the mean will be, and then we'll put it all on a picture. The middle 68% will be between 100 minus 16, or 84, and 100 plus 16, 116, and so we have the interval 84, 116. The middle 95% will be between 100 minus 2 times 16, so 100 minus 32, which is 68, and 100 plus 2 times 16, so 132. So in the interval 68, 132. Finally, the middle 99.7% will be between 100 minus 3 times 16, so 100 minus 48, which is 52, and 100 plus 3 times 16, which is 100 plus 48, which is 148. So here is what our picture will look like. We've got our IQ scores centered at 100, and we go out to 84 and 116, and that's going to have 68% of the area. What that means is the middle 68% of scores will be between 84 and 116. Area and proportion or percent are identical in this type of curve. Okay, so when we go out another standard deviation to our 68 to 132, we capture 95% of the area, which means we capture 95% of the scores. And finally, when we go out one more standard deviation, 52 to 148, we've captured 99.7% of the area, which means 99.7% of the scores. In what interval would you expect the central 95% of IQ scores to be found? We actually just determined that. Look back at the distribution and you'll see that our interval for that is 68, 132. About what percent of people should have IQ scores above 116? Okay, so here's 116, and we want to calculate the percentage of people who will have an IQ score above 116. So let's consider what we know. Okay, 84 to 116 contains about 68% of the scores, which leaves 32% of the scores in the symmetric tails. Okay, the upper tail and the lower tail are going to have the same percentage of scores. So we can divide by 2 due to symmetry, and we get 16%. So we have 16% down here and 16% up here. So above 116, we would expect about 16% of people. Now below 116, just for fun, we would do 68% for the middle portion plus 16% for this lower tail, and we would get 84%. About what percent of people should have IQ scores between 68 and 84? So this region right here, 68 and 84. Using the reasoning from the prior problem, there should be 16% of scores lower than 84. Now, we need to subtract off all the ones below 68. So we need to think through that. So 68 to 132 marks off 95% of the scores. So that means there's 5% left over. Divided by 2, it's 2.5%. So 2.5% of scores are lower than 68. And so we would do our 16% minus 2.5% to give us the 13.5% of scores between 68 and 84. You can see why it's helpful to draw a picture of the distribution before you start calculating percents. About what percent of people should have IQ scores above 132? Well, we just went through that. We do the 100% minus 95%. Okay, because 68 to 132 captures the middle 95%, and we get 5%. That is the area for both tails, so we're going to divide that by 2, and we get 2.5% for the lower tail, 2.5% for the upper tail. So about 2.5% of people should have an IQ score above 132. Okay, but what about scores that are not exactly 1, 2, or 3 standard deviations from the mean? Can we determine probabilities involving them? Absolutely. You need calculus, standard normal tables, or your CAS. We will use the CAS and let it do the calculus for us. All right, so the standard normal distribution has a mean of 0 and a standard deviation of size 1. And every single distribution every single normal distribution can be scaled or standardized so that it fits the standard normal distribution. Like I said, any normal distribution can be transformed by standardizing its observations. We call these standardized values z-scores. They tell us the number of standard deviations above or below the mean a particular observation lies. If an observation has a positive z-value, it's above the mean. If it has a negative z-score, it's below the mean. So the formula for this, for any observation x, can be calculated as follows. Z equals x minus x bar over sigma, or the observation minus the mean over the standard deviation. Okay, so based on the normal model, a normal distribution with a mean of 100 and standard deviation 16, describing IQ scores, what percent of people's IQs would you expect to be over 80? So our z-score is going to be our observation of 80 minus our mean of 100 divided by our standard deviation of 16. So we get negative 20 over 16, which divides out to be negative 1.25. Okay. On your calculator, you're going to go to probability distributions, and you're going to pick normal CDF. And our lower bound is going to be negative 1.25, and then our upper bound is going to be infinity. You can get infinity on your calculator by pressing the pi key that's right above the comma key, and when the pi key comes up, infinity will be one of your choices, so pick that. Leave the mean 0, leave the standard deviation 1 because we're working with z-scores, and the calculator gives you 0.8943506161, so rounding to the nearest hundredth of a percent, it would be 89.44%. Okay, so using the same scenario, what percent of people's IQs would you expect to be under 90? So we're finding, we need to find the z-score. So it's going to be 90 minus 100 over 16, negative 10 over 16, which reduces to negative 0.625. So again, you're going to go to probability, distributions, pick normal CDF. You're going to leave the lower bound negative infinity, and the upper bound is going to be negative 0.625, and so the calculator gives you the 0.265985 on and on. We're going to round to 4 decimal places, so 0.2660, and then convert it to a percent, so 26.60%. Okay, so now let's look, what if we want it between two values, 112 and 132? Well, we're going to figure the corresponding z-scores for both endpoints. So for our lower bound, our 112, we'll do 112 minus 100 over 16, which gives us 12 over 16, which divides out to be 0.75. And then for our upper bound, we are going to calculate our z-score. So 132 minus 100 is 32 over 16, divides out to be 2. And so, again, you're going to go to probability, distributions. You're going to pick normal CDF, and you're going to have a lower bound of 0.75, an upper bound of 2, and the calculator gives us 0.20387 on and on, rounded to 4 decimal places is 0.2039, so 20.39%. Okay, so unusual values and outliers. Any observation at least 2 standard deviations away from the mean in a normal distribution is considered unusual. Okay, they're not your typical values. Any observation at least 3 standard deviations away from the mean in a normal distribution is considered an outlier. So back to our IQ example, what IQ would you consider to be unusually high? So anything that's 2 standard deviations or more. So let's figure out what the first value for that would be. So 100 plus 2 times 16 is 132. I would consider 132 to be unusually high. Anything above it would be also. All right, so that's it. And go ahead and do the problems to try on your own. If you can't do those or you're really struggling with them, come see me. Otherwise, I will see you in class next time. Make sure you bring your CAS with you because you're going to need it. Have a good day. Bye-bye.